So this video is going to take a look at periodic trends and how the periodic table is arranged in the pattern that it is to yield these trends and the characteristics that we find within a period and within a group or family that contribute to these trends. Regardless of the trend we're looking at, when we are going across a period, we are staying within the same outermost shell when we're filling our electron configurations, but the protons are increasing in number as we move across, so that means our nuclear charge is increasing. As that charge increases, the nucleus is less likely to give up those outermost electrons. It will pull them more tightly to them. So this is what yields for some of our trends to require an increase in energy for electrons to be lost. It's what allows our atoms to become smaller as they go across. As we go down a group or family, we are adding layers of filled electrons. We're filling up our energy levels or shells. And the shielding effect becomes the dominant factor in determining our trends. As you go down a group or family, your nucleus is being further separated from those outermost valence electrons, and the nucleus is not able to exert as much of a pull on those electrons, and less energy is required for an electron to be removed. And it also impacts on the size of your atoms with those additional layers of electrons, and with the nucleus not able to hold on to the outermost ones as tightly, typically you're going to see your atoms get larger. And so that's the first trend we're going to take a look at, is atomic radius. Radius is just looking at the distance between your nuclei. As you go across a period, because of that increased nuclear charge, you are going to see that the radius is going to get smaller as the positive protons hold on more tightly. As we go down a family and we add those layers of electrons, the filled energy levels, we're going to see that the radius gets bigger as the nucleus is not as willing to hold on to those outermost electrons as tightly as it was going across a row. So here are some examples of atom sizes. We can see going down group 1 that cesium is our biggest atom within that group. Hydrogen is our smallest. And as we go across the row, we see that the trend is that the radius is going to diminish as we move from our metals over to our noble gases. The second trend we're going to look at is ionization energy, and this is yielding the amount of energy it needs to remove an electron from a gaseous atom or ion. When you're removing it from an atom, that's the first ionization energy. When you remove successive electrons from an ion, you get into second and third ionization energies. The metals tend to be very willing to give up their electrons. The increased nuclear charge is seen more on the non-metal side of the periodic table. So as we move across, we tend to require more energy to remove an electron, with the largest amount of energy coming from a noble gas, the one that is in the most stable configuration as an atom. When we go down a family and we add those energy levels, the shielding effect dominates, and the amount of ionization energy required to remove an electron diminishes. And this helps to explain why we tend to see our more reactive metals down into the left-hand side of the table, whereas our more reactive non-metals, the ones that are least likely to give up electrons and want to gain them, we tend to find at the top and right-hand side of the table. I said before that you'll see different terms for ionization energy. And again, that's based on whether you are going from a neutral atom to a +1 ion with the first ionization energy. With the second one, you're going from a +1 to +2, and we would keep going up with additional numbers of ionization energies. There tends to be a spike at some point in terms of where a great amount of energy is required to remove an electron, and those tend to be seen when you have reached the configuration that is comparable to a noble gas, or you have reached a configuration where you are semi-stable because each of your orbitals contains an electron. So when you have those filled or half-filled sets of orbitals, the amount of energy that is required to remove an additional electron is going to jump quite a lot compared to the other ones that you have seen before. So if we look at this graph, this is just showing the values of the first ionization energies for each of these elements. We can see as we go across period 1, hydrogen and helium, that there is definitely an increase. From lithium to neon, from sodium to argon, from potassium to krypton, from rubidium to xenon, from cesium to radon. We can also see more specifically with the noble gases, because they're going to require a significant amount of energy compared to our alkali metals. We can see that there definitely is a decrease in the amount of ionization energy required as we get further down that group of elements, group 18. And you'll see similar trends with the other groups. Electron affinity is similar to ionization energy, but we're looking at it from the opposite side. Ionization energy is when you want to give up an electron and make a positive ion. Electron affinity is when you want to gain an electron. Who wants to gain electrons? That's going to be your nonmetals, because they want to gain one or more electrons to become like the noble gas that's closest to them. Electron affinities are exothermic, so you're going to see higher values for your nonmetals because they're going to release more energy as a result of gaining that electron. Your metals tend to not want to gain electrons, so you're going to see either you're going to see positive energy requirements because they're going to need energy to be forced to add an electron, or you're going to see very, very small negative exothermic values. As we go down a family, again, the shielding effect dominates. We get further away from the nucleus with our valence electrons, and we will see that the electron affinity values are going to diminish. We're not going to release we're going to release less energy as we get further down because the nucleus just isn't going to care. So if we take a look at these values, again, we're looking at negative values because we're releasing energy. We see that fluorine and chlorine, fluorine is going to release less energy than chlorine does because, again, as we get further down, it just doesn't care. As we go across a group, we see that lithium to fluorine, lithium is going to release a lot less energy than fluorine would. Sodium is going to release a lot less energy than chlorine is. And again, that makes sense with our trend. We see more energy release as we move across and we get to atoms that want to gain electrons as opposed to our metals who do not want to gain them.